All right, let's do a related rates problem. The classic ladder problem, we have a ladder of length 12 feet that's resting against a wall. So the top of the ladder that rests against the wall is slipping down and the bottom is moving away from the wall. Okay, that's a lot to visualize. So step one on related rates problems, we'll always draw a sketch. Let's do that right now. Here's our wall. There's the ground. This is my ladder. The ladder has a length of 12 feet. And that's never going to change. So keep in mind, when we're talking about the ladder's length, that's just a constant. It's not changing as the ladder falls. Now we like constants because the derivative of a constant is always 0, so it makes our math a little easier. So if the ladder is 12 feet and the top of the ladder is slipping downwards, looks like that, and then the bottom of the ladder is moving away from the wall, so in that direction. First of all, let's choose some reasonable variable names to represent these changing values. So this distance from here to here is changing. Let's call that x. This distance, since it's up and down, let's call it y. We could call them anything, but these are variables that make sense to me. So if that's x and y, why don't we go ahead and call this r? Okay. Suppose that at a particular instant, the horizontal distance of the ladder from the wall, so this piece right here, the horizontal distance of the ladder from the wall, is increasing at a rate of 2 feet per second. So we're talking about the rate at which x is changing with respect to time. So dx dt, and it's growing. Since that distance is increasing, the rate of change will be a positive 2 feet per second. If the ladder was going this way, then the x distance would be shrinking. We would say that the rate of change is negative 2 feet per second. Okay. Also, the angle that the ladder makes with the horizontal, so here's the ladder, here's the horizontal. The angle that it makes there is, at a particular moment, pi over 6. So let's call this variable theta, and they're telling me that at the same time when dx dt is positive 2, theta is pi over 6. If I had said theta is changing at a rate, then I would have written d theta dt. But they're just telling me what theta is at a particular moment. And that would be measured in radians. Let's always keep our units nearby. Okay, so the question is, how fast is the angle that the ladder makes with the horizontal falling? Okay, that doesn't make sense. Angles don't fall. That's a typo. Change that to how fast is the angle that it makes with the horizontal changing. So translation, what are they asking us for in symbols? Well, how fast is the angle changing? They're asking for d theta dt. So look at what we're given. So let's go to step 2. We've drawn, we've labeled all the information. Okay, now let's do step 2, find a relationship. So we need to find a relationship between what they're asking us for, which is d theta dt, and what we're given. So I definitely need theta to be one of the variables in my relationship. They've also given me information about x, because they told me what dx dt is. So I want x to be part of my relationship. And what else have they given me info about? Well, it's not y. I know neither what the distance of y is currently, nor how it's changing with respect to time. So y will not be one of the variables I'll use. Instead, check it out, they told me what r is. So I'll use something that puts x, y, and r all together. What is that relationship? If you remember your trig formulas, it's going to be cosine. So cosine theta equals x over r. But remember, r is not a variable, so don't let it stay saying r. Change it to 12 because that ladder will never, the length of that ladder will never change. So now that we've found a relationship that puts everything that we need together, let's go ahead and do step 3. Let's differentiate both sides with respect to time. So remember, every variable, even x, will be followed by a d whatever dt. So d theta dt or dx dt. We're using implicit differentiation here. So the derivative of cosine theta will be negative sine theta d theta dt equals the derivative of x over 12. Well, let's bring down the constant first. Will be 1/12 and then dx dt. At this step, we should circle what we need to know, what they're asking us for. We want to find out what d theta dt is. That means that everything else in this equation should be already provided, and we should be able to plug it in. So let's see, do we know what theta is? Yes, we do. It's right here. Theta is pi over 6. Put a check mark. Also, do we know what dx dt is? Sure, that was the first piece of information they gave us. It's positive 2, so put a check mark. If all of the other variables are checked, you're ready to solve the problem. If you have more than one variable that's missing, or if you have one more variable that's missing, then you need to go back and either find a different relationship or a second relationship to get to the point where everything has a check mark. We got lucky this time. We're good to go, so let's plug in and solve. So we have negative sine of theta is pi over 6 times d theta dt equals 1/12, and then dx dt was positive 2. Okay, I'm going to make a little bit of room. Okay, sine of pi over 6, well, pi over 6 is just 30 degrees. So that's going to be 1 radical 3 and 2. And sine is y over r, so that's 1/2. So let's plug that in. That's negative 1/2. d theta dt equals 1 over 6. I want to isolate d theta dt, so what should we multiply both sides by? Negative 2. That cancels the 2, and the negatives go away. This leaves me with d theta over dt equals negative 1/3. Now keep in mind our units. Theta is measured in radians, so it's going to be radians, but it's with respect to time, so it'll be radians per second. And we're done. Now, just when you do a related rates problem, the advantage over like other type of problems is that you can actually check to see if this makes sense in the context of what's happening in the problem. So in this problem, take a look. Our ladder is falling, so let's see if our answer makes sense. As the ladder falls, what's happening to theta? Yeah, you'll notice that theta, that angle there, is shrinking. So that means that the rate of change should be negative, and indeed, our rate of change is negative. So we're good to go. Our answer makes sense, and we are satisfied. Let's move to part B. B says, how fast is the ladder falling to the ground? So this time, what are they asking us for? How fast is it falling to the ground? So they're referencing this distance here. How fast is it coming down? So that's dy dt, the rate of change of that vertical distance. Okay, so they haven't given me any new information. They're just asking me a new question. So let's see what relationship we'll use. Again, let's highlight what we know. Well, we need y. We need something that includes y for sure because we need dy dt. We also know we know something about x. We know r is 12. Okay, that's going to be a definite one in our relationship because it's a constant. So if we can keep it, we will. It makes our life a lot easier. And then, what else? Oh yeah, theta. So I definitely want y, I definitely want r. Now we have to pick between x and theta. I want you to think, how might we go about choosing which one? See which one you have more information about. So I'm going to make the case that, so I'm going to make my decision based on what information I have. Notice that for x, if I were to create a relationship that included x, then when I take the derivative, I'll have to plug in for x and dx dt. And if I use theta in my relationship, then when I take the derivative, I'll have to put check marks above theta and d theta dt. So let's see which one is going to be easier for us. We know what dx dt is because they gave it to us in the problem. But I don't know what x is. And it would also be pretty difficult to find x because I don't even know what y is. I couldn't even use the Pythagorean theorem to solve for x. So I don't know what x is. I would have to go about solving for it. And right now I don't know how I would do that. It's possible. It would just be an extra step. Whereas we definitely know what theta is because they gave it to us in the problem. And guess what? We just solved for d theta dt. So it will be much easier for us to choose theta and to leave x, to x out x. Okay, we don't want x as part of our equation. So let's come up with a relationship that puts y, r, and theta together. Again, another trig function. This time we'll use sine. So we're choosing sine theta, which equals y over r. Okay, let's differentiate. Step 3. So you can show that you're taking the derivative with respect to time on both sides like that, if you choose. Or you can just jump into it. The derivative of sine is going to be cosine theta, d theta dt. And if these are both variables, you'd have to use the product rule, low d high minus high d low, and all that jazz. But the good news is, remember, r is just a constant. So erase your r so you don't actually accidentally confuse yourself. Replace it with the constant that will never change, which is 12. And now we can easily take the derivative on the right side. The derivative on the right side is 1/12 dy dt. Let's again circle what we need. We need dy dt. And make sure we check off everything else. We know theta is pi over 6. We know d theta dt from our previous answer is negative 1/3. And now let's plug them in. So cosine of pi over 6 times negative 1/3 equals 1/12 dy dt. Let's find cosine of pi over 6 using the drawing we already made. Cosine is x over r, so it's going to be root 3 over 2 times negative 1/3 equals 1/12 dy dt. Multiplying straight across on the left side, I get negative root 3 over 6 equals positive 1/12 dy dt. I'll isolate dy dt and multiplying both sides by 12 over 1. That will cancel with the 6. And my final answer is dy dt equals negative 2 root 3. Let's get some units. When we're talking about the rate at which this is changing, we're describing feet. Right? Y is measured in feet. But it's with respect to time, so we need our time as well. That's feet per second. And we're done. But again, we have to make sure that this makes sense. So go back to the problem. Check if the sign makes sense. So if there's a negative, that means that the y distance should be decreasing. And indeed, as the ladder falls, the distance of y does decrease. So it makes sense, and we can feel confident about our answer.